Hi there, in this video we're going to look at the unit step function. Okay, so the idea of unit step function is that it's, if we take an axis, okay, then for values of t less than 0, it is 0, okay, so it's just 0 here, off to infinity, and for values of t greater than or equal to 0, it's got a value of 1. Okay, so it's quite a straightforward one. So we can write u of t equals 1 for all, the upside down a means for all t greater than or equal to 0, and it equals 0 for all t less than 0. Okay, so that's us defined our unit step. Okay, so that's got a height of 1, and we usually call it, see it called u of t. Okay, now we can't go and find the Fourier transform of that, okay, because it turns out that this integral, when we try to work it out, won't converge, okay. So what we do is we make it up using another couple of functions, okay. So what we do is we produce this step function using this function here, which is just a line of height a half, okay. So that's one function there, and that's a function of t, and we add on to that a function called it's a signum function, but it's actually half of a signum function. So the function there, it looks like this. It's very similar. It looks like that. Okay, so that height there is a half, and that height there is minus a half. Okay, so when you add this to this, you'll get a half plus a half, so you'll get 1, and you'll get minus a half plus a half, so you'll get 0. Okay, so we get 0 back here. Okay, so that there gives us our function. So what we do is we say u of t equals half plus a half, and it's just, we call it SGN for short. Okay, that's signum. Okay, so the signum function, which we're going to go and have a wee look at just now, and we're going to be using that in order to work our way back and find this Fourier transform. Okay, so that there is how we are going to work out our Fourier transform, because in effect we'll work out our Fourier transform for a half, we'll work out our Fourier transform for our signum t, and when we add them together we'll have a Fourier transform for our function u of t. Now we only have that because of the linearity of the Fourier transform, which is a basic principle, and I'll go back to when we look at the properties of the Fourier transform in the next couple of videos. Okay, so first of all we'll look at this signum function. Now the signum function looks like this. Okay, now it's not actually defined at 0, okay, so I'll put an open circle, okay, but that's height 1 and that's height minus 1, and we say the signum function of t, like that axis t, well, equals minus 1 for t less than 0, and it equals 1 for t greater than 0. Okay, so no, it isn't actually defined at 0. Now again, we can't find the Fourier transform for this because again the Fourier transform won't converge, but with this we can find a function that's very similar to this. Okay, so the function will look like this. If we say that's t, then we can create this function here, which I'll just draw in. Okay, and a function there. Okay, now this function here at this end here, that's e to the minus epsilon t and this function here is e to the epsilon t, and it's the negative. Okay, so we know that a function e to the x, I'll just draw in quickly so we get a grasp of these. Our function e to the x looks something like that. Okay, that's e to the x, right, or e to the t, we'll just use the same t. There's e to the t there. Okay, now all the factor epsilon does is just is a factor that will change the scaling on this. Okay, so if we look at e to the t, okay, and if we take the negative of e to the t, well, that's equivalent to flipping this over this axis, so you just get something that looks like this. Okay, now we've only defined that, we're only defining that for values of t less than 0. Okay, so we're just going to get rid of that part of it. Okay, so I'll just get rid of that. So we're getting rid of the part of it that's positive. Okay, so we're only left with just this part, the negative part, okay, which is this negative part here. And the same for the positive. We've got e to the negative t. Well, e to the negative t actually looks like that. Okay, so it comes in that way. Okay, so it's e to the negative t, but we're only going to define that for values for t greater than 0. So we're going to get rid of that little part of the graph there. Okay, so you're going to just end up on that end there. You're just going to end up with this section here. So you have that section there and that section there. Okay, and that's what you see here. So let's just write that out. I'll get rid of this. Make the rubber a bit bigger, so quicker. There we go. Got rid of that there. Now, so let's write out the signal function. So the signal function, no, this function here, sorry, is defined as minus epsilon minus e to the epsilon t, okay, for t less than 0, and it's defined as e to the minus epsilon t for t greater than 0. Okay, so that's us defined that function there. Now the reason for defining that function is that we can integrate this function, okay, and means we can find the Fourier transform of that function. So, but this function here, as we let epsilon tend towards infinity, so if I say the limit as epsilon tends towards infinity of this function here, we'll call this function g of t, okay, equals this signal function. Okay, and we can see that there because if we let epsilon there tend towards infinity, then you'll have an infinitely small value. Okay, so that's going to tend, let's see, I guess again. So if we let epsilon tend towards infinity, yeah, we're going to have an infinitely small value. So if we have e to the 0, n raised to the power of 0 is just going to be 1. Okay, so that will tend towards that positive 1. Okay, and in our case here, as we let epsilon tend towards infinity, then this is going to function here, okay, again is going to tend towards 0, so that e to the epsilon t will tend towards a value of minus 1. Okay, so that will tend towards this minus 1 here. Okay, so if we take that limit as epsilon tends to 0 of this function here, which we can call that function there, which we call g of t, will give us the signal function here. Okay, now as I say, the reason for doing that is because we can find the integral of that function. So let's go ahead and we'll just do that just now. So what we're looking to do is find, now it's two integrals, so it's an integral from minus infinity to 0. Okay, so we'll split into two, so it's going to be the integral from minus infinity to 0 over function, so that part of the function is the minus e to the epsilon t times e to the minus j omega t, that's us just taking the Fourier transform of it, okay, by dt, and we're going to add on the Fourier transform for this function here, which will be the integral from, now the limits are going from 0 to infinity over, and it's the e to the minus epsilon t times e to the minus j omega t by dt. Okay, so we know that we're saying here that the f of j omega equals that. So from that we can then say we gather our terms again together, minus infinity to 0 of e to, and that would be epsilon minus j omega t by dt plus the integral from 0 to infinity of e to the minus, and it would be epsilon plus j omega t by dt. Okay, now when we differentiate with respect to t, this just looks like a constant. Okay, so that's going to come down, so you're going to end up with minus 1 upon epsilon minus j omega. Okay, now the limits of the integration ensure that we only have a value, one value here, okay, because when we put the value of 0 in for the t, we'll just get 1, and we can put the value in for minus infinity, we'll get 0. Okay, so we just end up with a constant factor on this integration there. Okay, and if I add on the next one there is 1 upon epsilon plus j omega, and the same thing goes the rest of the integral, e to the epsilon plus j omega will just tend towards 1 when we put the limits in, because we've got 0 which will give us a value of 1, and we've got infinity that will give us a value of 0. Okay, so we're just left with these here. Okay, unsure of that, it's just a wee read over, and it's all kind of bookwork as well. You'll find this in quite a lot of the books. So that's us got this here. Now what we want to do is we want to take the limit of this, okay, the limit as epsilon tends to 0 of that. I'm just off the edge of the page there, so I'll just move up a little bit. So we want to take that limit there, so in effect epsilon tends to 0, so that's got to tend to 1 minus 1 upon minus j omega plus 1 upon j omega, which equals, well, a minus and minus adds up, cancel to make it a positive, so you're going to have 2 upon j omega. Okay, now that can be written as, if we take the j up, it will be minus j2 upon omega. Okay, so now what we can do is we can have a wee look at that. I'll put it on the next page and we can get it up in MATLAB, and I'll have a wee look at that. Okay, right, so let's back up here. Right, now I'll rewrite that little section again. So we're really saying that when we take the Fourier transform of that signum t function, okay, this is another transform pair, we're going to get minus 2j upon omega. Now let's have a wee look at that in MATLAB. I'll try and bring this up. I've got it sitting somewhere. Signum, is that it's signum. Okay, now let me get MATLAB up here. Okay, right, come on then. Oh, there we go. Right, sorry, wait, that's me. Okay, I think you can see that there now, so I'll bring that up. So what I've got there is that signum function. Okay, so that's going from -1 up to +1. Okay, and it's the cutoff there is at 0. Okay, so it's changing at that point 0, and I've the top one here, so that's the time version. That's what we're going to do the Fourier transform on that, and that's what we get. Okay, in MATLAB, and I've done it in 3D. Okay, so you've got the imaginary part and the real part. Okay, so that's the real part up there, the imaginary part there, and that's the frequency along the axis there. And you notice that this is a purely imaginary value. Okay, you look at it, it's purely imaginary, there's no real part to it. Okay, now, and you can see then that this is given as our minus 2j upon omega. So you can see that that's really, when you say it's minus 2j upon omega, it's just like saying minus 2 upon x. Okay, now if it was say 1 upon x, well, if we bring it up like that there, yeah, I'll write this down when we get back into our page, but 1 upon x, you could say, if x tended towards 0, 1 upon x would tend towards infinity, and if x tended towards 0 from the other side, x would tend towards minus infinity. Okay, but it's not 1 upon x, it's minus 1 upon x, so it's that same graph but flipped on this axis, so you end up with this sort of graph here. And the reason you got all the wee blips there and it's not a perfect graph is because that's not heading off to infinity, that stops at 20 and minus 20. Okay, so that's how you get all these extra little blips, but you can get the window of the minus 2 upon omega axis function for that there. Okay, so let's go back and we can write that down there. Just let's have a look and put it in a smooth draw. There we go. Okay, so what we said there really is we found the Fourier transform of the signum function. We've got that there, minus 2j upon omega. The j just tells us that it's it's purely imaginary, so it's on the imaginary axis, and that's just like saying if I had a function, if the function was 1 upon x, so as x tends to 0, this whole thing tends to infinity, and as x tends to infinity, the whole thing tends to 0. So 1 upon x would look like that, and again it would look like that on the negative side, but it's not 1 upon x, it's minus 1 upon x, so it's like that graph flipped on this axis. So you're actually going to get that. Okay, so this has been flipped up there and it's been flipped up there. Okay, so that's what we're actually seeing, and the factor of 2 is just a scaling factor, so it just gets the same sort of thing but just scaled a little bit. Okay, and the j just tells us that it's purely imaginary, and that's just what we've seen in that last in the MATLAB. Okay, so I think that's quite useful. I learned quite a lot of it from putting things in MATLAB. So let's continue. We've got the Fourier transform of our signum function. Now, if we want to find the Fourier transform of our function, or step function, as you remember it was u of t equals a half plus a half signum t. Okay, so it's going to be quite straightforward now, because we know if we find the Fourier transform of a half. Okay, so that's just a half. Okay, and that's in the time domain. When we find the Fourier transform of that, all we're going to get in the frequency domain there as an impulse. Now it's not going to be a height of 2 pi because it's only a value of a half, so it's going to be a height of a pi. So you're going to have a pi times an impulse in the frequency domain, pi delta omega. Now the signum function is going to be the half signum function is going to look like that. Okay, and the Fourier transform of that signum function is well, it's what we just seen in the graph there, so it's something like that. Okay, and it's got a, if that's the imaginary part, it's going to, that's omega, it's going to have some function that looks like that. Okay, that's what we just seen a minute ago on MATLAB, and we know that the value of it, well, we've just worked it out. Worked it out up here. It's going to be minus 2 upon j omega. Okay, but that's for a full signal function, which is height 1 and minus 1. This is only height a half and minus a half. Okay, so it's a half the signal function. So the Fourier transform of that signal function then is half a signal function is just going to be the, if we put in minus 2j upon omega, it's that times a half, that equals minus j upon omega. Okay, so that's us worked out the little section there for that. Now what we can do is we can say that minus j can actually be written as, if we want to write it in, we can write that as equal to 1 upon j omega. Okay, and the negative will come down. Okay, so you know, we can get that because j times j equals minus 1. Okay, so then you can say that j equals minus 1 upon j. Okay, so that is equivalent to saying that minus j equals 1 upon j. Okay, so that's just a little bit there. I'll rub that out so that it doesn't mess it up. Okay, so that's us got, that's us nearly there. So we can then say that our Fourier transform over u of t is going to equal the pi delta omega plus 1 upon j omega. Okay, so that there is our Fourier transform. Now let's have a wee look at it in MATLAB, and it'll all become apparent where that comes from. Okay, so I'll bring up MATLAB again. Okay, I'll bring up MATLAB and we'll have a little look, and let's just see if I can, I'll find it here. Just bear with me a second and I'll unit step. Now let's look. We'll try this again. MATLAB. Okay, that's us. Right, good. Right, now this is just about done. So now what you see here is that unit step starts at 0, goes up to 1. Okay, that's the time domain, and here's a frequency domain version up at the top. Okay, now you look at it like that just now and it looks just like gobbledygook. You think, well, what's that telling us? And the beautiful thing about doing it here in the 3 dimensions is that I can come round like this. I can, well, let me just undo, edit, undo the pan. I want to rotate. Okay, so I can rotate it like this, so that all I'm looking at here is the purely real axis. Okay, so I'll put it a wee bit further, there we go. So that's the real axis. Okay, so the real axis there is given as an impulse. So that's our pi delta omega. Okay, obviously I've got a value of 20 because none of this has been normalised, but it gives you an indication of it. Okay, so that's a pi delta omega section, which is the purely real section, and the imaginary section, well, I'll just turn it round this way here, and you can see it. Look at, there's it in 3D. I turn it round like this. Okay, and let's get the imaginary section all the way around, and bam, there we go. That there is our 1 upon j omega. Okay, right, so that's it there. Okay, so that's all there is to that at the moment. Okay, I'll go on and look at some other functions in the next video. Okay, so thank you for listening, and goodbye.